Origami-inspired robots have drawn immense attention in recent years for their wide range of medicine and engineering applications. While they thrive high on their shape-morphing advantages, pose estimation of origami robots remain a challenging problem. Pose estimation and tracking are vital to study, control, and automate this deformable body locomotion. A solution is to develop a deep learning-based pipeline that can effectively estimate the pose and get the shape information of the deformable origami robots. This paper proposes a self-supervised learning-based algorithm named ScoopNet that trains on a synthetic dataset generated from simulation to infer the robot's pose and shape. The key contribution of the paper are 6DOF pose estimation of origami robots, synthetic dataset generation, shape prediction using semantic segmentation. The ScoopNet architecture is inspired by residual learning and UNet. The input of the network is a real-world image of an origami. The ResNet encodes image into a lower dimensional latent space. A series of fully connected layers are added to get the pose of the object. The latent space is reutilized to get the shape of the origami. The UNet decoder uses latent space to generate a semantic map. This is the full ScoopNet architecture. Moving on to the result section, the left bottom video is the real-world footage which is passed into the network. The right video is a segmentation map obtained using ScoopNet. The middle video is the visualization of the pose obtained using the simulator. A filter was applied to smoothen the camera motion for better viewing. We showed that the network is capable of tracking multiple shapes of origami with great accuracy for both pose and segmentation. Next, we show how simulated data was generated. This is the setup of origami in Rhino Simulator. The fourth octant is denoted by green colored part of the sphere is the region of interest, as this part was used for data generation. We use this to avoid the problem of symmetry. The 250 blue dots correspond to various camera positions in the region of interest. The 20 red dots correspond to the camera target or the location that the camera sees. In addition, there are 6 in-plane rotations considered for every camera position. The plane shown here depicts the camera plane with the x and y axis shown by red and green lines respectively. From the previous slide, we can conclude that the pose estimation of non-rigid body was possible by using self-supervised learning method with synthetic dataset. Only one network was sufficient to give both shape and 6 DOF pose of the origami. The new dataset generation method ensured proper variations. Furthermore, domain randomization was used to have a better dataset diversity.